Well, we have a capacitor. We have the capacitance of that capacitor defined in terms of the geometry of that capacitor for a parallel plate capacitor. Now, we also have a relationship such that the charge stored on a particular capacitor is equal to the capacitance times the change in electric potential over that capacitor. Now, any sort of approximation breaks down at some point. But physics, science in general, is built on models. So I'm going to use a model here to explain what's going on. And in order to really point out that it's a model, I'm going to make this ridiculously, to the anthropomorphized, just to hopefully illustrate that, oh, by the way, this is a model. Now, let us envision a capacitor. We start off establishing a change in electric potential over that capacitor such that, let's see, so if I establish some change in electric potential between those 2 points, what that means is that I'm generating an electric field in the wire, which means that I'm generating an electric force on any electrons that travel. So let's take Ted the electron acting under the electric force, moving along the wire. So this electron will come, it will reach this point. A negative charge will stick because the electric field has to be quite large, certainly not much larger than you want for your electronics, before the electron, or with a bunch of little friends, can jump the gap. In fact, that's very bad if that happens. But if I have a piece of negative charge here, from what we've done before, that will induce a positive charge on the opposite plate. And since I'm not creating charge out of nothingness, that's going to knock an electron free. So if I just look at this in terms of, hey, big black box, what's going on here? I see an electron go in, and I see an electron come out. And there's no way to tell this electron from that electron. So at the very beginning, oh hey, an electron came through. But now, let's look at the second electron. As the second electron is moving in this direction, it's feeling a repulsive force. Due to that negative particle. It's feeling an attractive force that's less, because the attracting positive charge is farther away, to this little positive hole on the other side. And it's feeling an electric force because of the electric field established in this wire caused by the difference in electric potential over the wire. So this second electron will hit and stick to that plate, but each electron, and freeing up another positive charge, freeing up another electron, but each electron that keeps moving through is going to continue to you're going to find at a certain level, well, each electron is going to be slowing down basically, as it were, to come to this plate. So it's going to be a smidgen more difficult for each, as more and more charge gets added to the plate, the flow of charge onto that plate is going to get less and less and less. And in fact, I'll look at how that changes over time when we get into current a couple of chapters from now. So, one thing that I can say is that at the end, when this builds up, if I have, say, a capacitor with a capacitance C, and I connect that over some source of some forced change in potential. What are we going to use to force that change in potential? A battery. And the change in potential over that battery is written as script E and spoken of as the EMF of that battery. What does EMF stand for? Right now, EMF stands for EMF. It used to refer to electromotive force, but it's not really a force. But everybody got used to calling it EMF, so EMF it is. It's a change in potential. And then, at the end, if I just have a battery connected to a capacitor, then charge is going to build up on the capacitor until the change in potential over that capacitor is equal to the EMF of the battery. More detail about this in the next chapter.